Welcome everyone. My name is Christopher Kuhn. I am researching failure prediction in autonomous driving at both Technical University of Munich and the BMW Group. In this video, I will introduce you to our approach to failure prediction for the task of semantic image segmentation. So why would we want to predict failures in semantic segmentation? In autonomous driving, accurate semantic segmentation is a crucial component for allowing accurate scene understanding. Despite recent progress in this field, failures are, however, inevitable. In order to make safety-critical driving decisions, it is essential to know where the semantic segmentation can be trusted and where it is likely to fail. There are already several approaches that allow to assign uncertainty to a model's prediction. However, they are not designed to predict failures explicitly. We propose to do just that. Our idea is based on recording errors made by a given semantic segmentation model and then using those failures as training data for a dedicated failure prediction model. This concept is called introspective failure prediction, which we apply to the task of semantic segmentation in this paper. First, let's look at related works in this area. We briefly show three important concepts here. First, there is Monte Carlo dropout. MC dropout allows to estimate the uncertainty of a given trained neural network that contains dropout layers. The idea is to keep those layers active during testing and then perform multiple forward passes with different dropout masks. This leads to a distribution of, for example, up to 100 predictions, and the variance of those can be used as a measure of uncertainty. In the picture, you can see this concept applied to semantic segmentation. The misclassified car to the left is correctly estimated to be very uncertain. Another idea is to use deep ensembles. Here, different predictions are obtained by training an ensemble of, for example, 5 models with different random initializations. The variance of the resulting predictions again allows to estimate uncertainty, requiring only 5 inferences instead of up to 100 per input. However, those methods cannot deal with consistently overconfident but wrong predictions. A drastically different approach is to train a complementary second model with failure data obtained from the first. This idea is called introspection. It was first used to train such a second model with video sequences of a drone crashing. The resulting model was able to detect spatiotemporal features that indicate the drone is about to crash, allowing it to reduce the number of crashes significantly. We propose to transfer this idea to semantic segmentation and extend it to pixel-wise failure prediction instead of assigning the entire input a label of failure or success. Here we show an overview of the proposed pipeline. Our approach is based on predicting the failures of a given semantic segmentation model. For this, we use a baseline semantic segmentation model and predict pixel-wise labels for a set of images the model has not been trained with. For each image, we therefore obtain pixel-wise error maps, which indicate where the inspected baseline model has failed and where it has accurately classified each pixel. This leads to a set of images as well as a set of binary error maps. We propose to use those error maps as new labels for those images to then train an introspective failure prediction model. Instead of predicting semantic classes, the introspective model only predicts a binary success or failure classification for each pixel. For each new test image, the introspective model can then predict where the baseline model will make mistakes. Next, let's focus on the specifics of how to design and train such an introspective model. A key insight of our approach is that the task of failure prediction can be considered as a special case of semantic segmentation itself. Instead of predicting semantic classes based on visual features, we want to predict failure or success based on visual features. We therefore propose to use the same encoder-decoder structure used for the semantic segmentation model for the introspective model as well. In fact, we can efficiently reuse the entire implementation of the inspected baseline model. By reusing the architecture, we can also share the low-level layers with the baseline semantic segmentation model. This improves training and inference speed of the introspective model, while allowing the introspective model to learn from the encoding of the inspected semantic segmentation model directly. The introspective model then only has to learn how to decode the encoded input image into a binary predicted error map. With the architecture and training scheme selected, the next step is to obtain failure data to learn from. For this, we propose the following split of a given dataset of images that have pixel-wise class annotations. From the training set, we use 50% to train the baseline semantic segmentation model. We then use this baseline model to obtain pixel-wise predictions for the second 50% of the original training set. For this second half, we use the pixel-wise prediction errors of the baseline model as new binary labels. We then train just a new decoder with the second half of the images and the pixel-wise errors as labels. Finally, the testing set can be used both for testing the baseline semantic segmentation model as well as the introspective model. We obtain the actual error maps produced by the inspected baseline semantic segmentation model and compare them to the predicted error maps output by the introspective model. This allows to evaluate how well the introspective model manages to predict pixel-wise failures. Now let's go through the specifics for how we experimentally evaluated the proposed approach. First, we trained our models. For all experiments, we use the large-scale A2D2 driving dataset, which consists of over 40,000 natural driving images with pixel-wise annotations of 38 semantic classes. With 16,000 images, we train a baseline semantic segmentation model. Due to its state-of-the-art performance, we select a DeepLab v3+ architecture for this task. Then, we train a second decoder with another 16,000 images. 4,000 images are used as a validation set for both training procedures. For the second introspective decoder, we use the error maps obtained by the DeepLab v3+ semantic segmentation model as new binary labels. As reference state-of-the-art approaches, we use MC dropout with 40 forward passes per image, which does not require any additional implementation. We also implement the deep ensemble approach by training another 4 DeepLab v3+ baseline models, using the variance of the resulting 5 models as the uncertainty estimation for the baseline semantic segmentation model. In order to evaluate both the reference approaches and the proposed introspection idea, we perform a precision recall analysis to investigate this binary classification task. We use the remaining 4,000 test images for this. Finally, we also want to visualize the performance of the different methods to give further intuition about how the models perform. Here we show the results of our experiments. To the left, you can see the average image-wise precision recall curves for the 2 reference approaches as well as the proposed introspection method. The proposed approach visibly outperforms both reference approaches. When comparing the area under curve values, introspection outperforms MC dropout by almost 7% and outperforms deep ensemble by over 3%. To the right, we also show the class-wise results for some select classes. For common classes like car, introspection performs best, as it has seen such features often in its training. For rarer visual features like dashed line, A model-based uncertainty measure like Deep Ensemble performs better, since introspection has not seen enough images of such a rare class to properly learn about its failures. This class-wise evaluation shows introspection and model-based measures like MC Dropout and Deep Ensemble have different strengths. We therefore combine both ideas in a final evaluation by averaging the predicted failure probability of introspection and MC Dropout or Deep Ensemble. The results are shown as well. In fact, the combination outperforms any individual method. Adding the predicted probability from introspection to the output of MC Dropout leads to an improvement of over 8%. Adding it to Deep Ensemble leads to an improvement of over 7%. This demonstrates how complementary the proposed approach of introspection is to existing works in the field of uncertainty estimation and failure prediction. Lastly, we would like to show what the failure predictions by the different methods actually look like. To the left, we have the original image, then we have the actual error made by the inspected semantic segmentation model, and then we have the predicted failures by the three investigated approaches. We can see that MC Dropout mostly outputs sharp edges as failure predictions, allowing it to correctly detect class boundaries as errors. Deep Ensemble is additionally capable of predicting entire patches to be incorrect, but the output is visibly fragmented as only 5 values are used to compute the variance, leading to an overall low range of different possible scores. Finally, introspection is capable of both predicting the class boundaries as problematic, as well as classifying entire regions to be failures. For example, the head of the pedestrian in the middle row. This highlights the fact that introspection uses visual features to determine failures, allowing for entire patches of problematic visual features to be predicted to be failures. The visual differences again show how combining the different approaches can lead to the best results, as visibly different sources of errors are detected. In conclusion, let's summarize the key insights of this work. Regarding failure prediction performance, introspection significantly outperformed existing state-of-the-art methods. The area under curve of a precision recall analysis was between 3.2 and 6.7% higher than existing approaches. Combining introspection with existing methods allowed yet another improvement of 3.7%. At the same time, the introduced computational complexity is very low. By resharing the encoder with the baseline model, only a single additional decoder has to be evaluated for each input image. This is in contrast to MC Dropout, where the model has to be evaluated 40 times to obtain the shown results. For deep ensembles, we still need 5 entire forward passes. And whereas we need 4 entire additional trainings for deep ensemble, our approach only requires training 1 more decoder, which is significantly faster than training even 1 additional entire model. In summary, our approach offers significantly better performance at the cost of less than 1 additional forward pass, making it a promising candidate for applications such as autonomous driving, where real-time capabilities are essential. In future work, an interesting idea would be to explore a better data split of the training images between the baseline and the introspective model. In this work, we used a 50-50 split. But we could also explore using less data for the introspective model, since it reuses the encoder of the baseline model anyway, which would allow the baseline model to have more training data to learn from. Finally, an interesting next step would be to extend this approach to taking video sequences as input. This could allow temporal features to be used to improve introspective failure prediction for semantic image segmentation. Thank you very much for taking the time to watch this video about our research results. If you have any questions, comments, or feedback, we would love to hear from you, so feel free to get in touch.